All right, two more important observations from these plots, specifically the left plot we're talking about. We're not very focused on the phase plot at this point, or at least in this course. Just put it there so you see how theta also changes, and that actually is important again when it comes to controlling the system. Now, one thing I want you to pay attention is that if you look closely, let me use a different color. Look at where the maximum values are for any given damping ratio, which is a damping. The maximum for z equals to 0.1 is here, maximum amplitude. The maximum for z equals to 0.3 is around here. The next one is here. You know, it slightly start becoming flat. But if you connect these maximum values, let me use a color that is, connect these maximum values, you'll get a line like this. What does this tell us? It tells us that the maximum, or the place at which, or the frequency ratio at which the maximum amplitude occurs is not the same as resonance. So at resonance, when we had a spring mass system, the maximum amplitude was happening where the resonance was, meaning that whenever the excitation frequency and natural frequency were the same. But when we have a spring mass damper system, the maximum amplitude does not occur or does not happen. And maximum amplitude here we're referring to M. It's just a non-dimensional number representing the magnitude, the amplitude. It happens at a different point. Now, where that point is, I'll tell you next. But let's see first where it happens. Some value R, right? It happens at some value R, depending on what is the damping ratio. And you see when we increase the damping ratio, it gets farther and farther away from the resonance. So for any given damping ratio and frequency ratio and damping ratio, the maximum amplitude happens at a specific place. Or maybe I have to, that was a wrong statement. For any given damping ratio, the maximum amplitude happens at a different frequency ratio. So if you have a specific system, frequency ratio is fixed. Omega excitation frequency, let's say is 10 radian per second. Omega n is fixed value. Spring stiffness and mass are fixed. If you change the damping ratio, which means you're changing a damping, the point at which the maximum amplitude occurs changes. And it gets, if you increase the damping, it gets farther and farther away from resonance. If there is no damping at all, it happens at resonance. If there is damping, it gets farther and farther away from resonance. So let me phrase that statement. I think the point, I actually lost which point. 4.4. Now for zeta greater than 0, smaller than 1 over square root of 2. Where did I get that? It's about 0.71. Well, the problem is if the damping is greater than 0.7, 0.71, 0.72, 1 greater than 1 over square root of 2, you can see in this graph, if I increase the damping too much, there is no maximum. Right, let me clean up here. If I increase the damping, as you can see, the magnitude, the amplitude is becoming flat. And at 0.8, for instance here, which is greater than 0.71, you see the plot is kind of flat. There is no maximum. So in order to have a maximum amplitude, we have to have a damping ratio which is less than 0.71. It's a number I gave you, and that's where it comes from. So if the damping ratio is Some verb greater than 0 and smaller than 1 over the square root of 2. If it's 0, it's an undamped system, a spring mass system, so the maximum occurs at resonance anyway. So anywhere in this range, we say the maximum value of M, which is a representative of the steady state response magnitude, occurs when R is equal to square root of 1 minus 2 zeta squared. If you rewrite this as knowing that R is equal to omega over omega n, then you'll get omega equals to, or omega, let me call this R max, wherever the maximum happens. Right? Omega, well, maybe R max is not a good representative because it's not the maximum R. It's where the maximum M occurs. So keep that in mind. That omega at which the maximum amplitude occurs becomes 1 minus 2 zeta squared. This is an important observation. Why? Because when you're designing a system, one of the things that you keep in mind is that to make sure that you minimize the displacement, right? The vibration, the amplitude of the vibration in your system because of some environmental vibration. You want to minimize that. So you want to stay away from this. This is where the maximum displacement happens for a given damping for a system. Right? And this value is lower than both natural frequency, obviously omega n, because number smaller than somewhere between 0 and 1. Imagine, remember, zeta is a number between 0 and 1. Typically, here is even smaller than 0.7. So this is a number smaller than 1, the whole thing. So this means that obviously omega is smaller than natural frequency, and omega is even smaller than this specific omega. I guess I'm just going to go with max, but just keep in mind that this max means where the maximum amplitude occurs. It's even smaller than omega d, damped natural frequency. Remember, omega d, what was omega d? Omega d was square root of, omega d was omega n square root of 1 minus zeta squared. This is even smaller than that. So this specific frequency, which is the frequency of excitation, let me write it down. This occurs when omega is this, and then which is smaller than or lower than. It's more meaningful to use lower than, low frequency, lower than the undamped natural frequency, or just natural frequency, in parentheses omega n, and damped natural frequency. Just going to put it here, which is omega d. Wasn't a good one. Damped natural frequency, which is omega d. So important observations and insights we're getting that we could never get these insights about the system and how does it behave under different conditions if we were just looking at the equation, system response. Lastly, I'll tell you what the maximum is. The maximum value, right? That's the frequency at which the maximum happens. Now, the maximum value of x, obviously, I'm going to put it as when R is equal to 1 minus 2 zeta squared. That happens at that frequency ratio is given by, I'll just give it to you directly. You can find it. You can actually, theoretically, you can just plug in the values and find this number or this expression. So it happens M max, this actually makes sense, that the maximum value of amplitude ratio is 1 over 2 zeta square root of 1 minus zeta squared. Very important observation. Another important observation. So we figured out where the maximum amplitude occurs, and also what is the maximum amplitude at that given at that specific frequency ratio. These are the last two observations. Before that, we looked at the system, and also we observed some patterns. Later on, when you want to design something, obviously, if you want to play around, increase or decrease the amplitude for a given damping ratio, you just take a look at these results, the plots, and the conclusions we made from these results. Right? It helps a lot.